And so does everybody see the screen? Is everybody okay?
Yeah.
Okay. Okay, so here we go. Oh, by the way, guys, I leave the captions or the subtitles. Does this bother people at the bottom of the screen? Do you want me to leave this on the PowerPoint, or do you want me to remove it? Is that okay? Because sometimes people can see what I'm saying. I find that it's pretty good, the voice recognition. So if this is bothersome, let me know and I can just turn off the subtitles, okay? Okay, so here we go. Structural analysis. Now, simple question. And here you go. What is structural analysis? Does anybody want to venture a guess? And guys, trust me, there's no wrong answers. So what do you think structural analysis is all about? Does anybody have an inkling? Guys, look, you have absolutely no idea what structural analysis is all about? Well, believe it or not, in your physics class, you've already done some structural analysis, okay? Now, basically, okay, what you do with structural analysis is that you're trying to determine the internal forces of a structure, remember, caused by the loads and effects. So you guys have done moment diagrams in physics, right? You've done shear diagrams, okay? Well, you've done analysis. In other words, based on the loading that your member was subjected to, you were able to determine the internal forces that the beam was going to have to develop in order to keep everything in balance. So does everybody understand what I mean by internal forces? Okay, let me share something with you that, okay. I'm going to draw something here very quickly. Here's a beam, right? And here's a load. And here's a support, and here's a support. Everybody recognize what I'm drawing? Okay. Now, when you were doing in physics, they told you, well, calculate the reactions here. They told you to calculate the reactions. That's what you did, right? So you calculated the reactions. And then they asked you to draw a shear diagram, and they asked you to draw a moment diagram, okay? This is what you ended up doing. Now, what do you think that this diagram represented, the shear diagram, and the moment diagram represented? Did they explain to you what this, did they explain to you what this was? Did anybody, like, you guys, you've all done shear diagrams in physics, right?
Yeah.
And you had no inkling what you were doing, is that it?
Well, that is bending moment diagram.
Okay, but what is the bending moment diagram? Go for it.
To show how much bending it is.
Well, okay. To show how much bending. So how much, and what does how much bending represent? Okay, let's start with this. I want you guys, because if you guys understand this, you'll understand what analysis is all about, okay? Now, let me just erase this, okay? Let me erase this, and we're gonna, so you guys did shear diagrams, you did moment diagrams, and the physics teacher did not explain to you the objective of doing this, right? Now, now, if I look at this beam, okay, you guys like numerical values, okay? So let's say, well, I mean, like here, I have a load here, okay? W, 10 kilonewtons per meter. And here I have a span, oops, sorry, I should, of 10 meters, right? So you were given, and then of course here they represented this as you had a roller there and you had a pin support there, and we'll talk about this so you have a better understanding what this is all about. And then they said, well, calculate the reactions, and then you ended up getting like R1 was equal to 50 kilonewtons, R2 is equal to 50 kilonewtons, okay? And then after that, they said, well, draw the shear diagram. So what you guys did is you drew a line, and all of a sudden you came up to 50 kilonewtons here. And then you went across and you went all the way down, and then you came back up to 50 kilonewtons there. And that was your shear diagram. Everybody remembers this? Okay. Now, what do you think the shear diagram represents? Or what is the shear? This is your shear. Okay. What does the shear diagram represent?
Well, to show the shear force along the beam.
Okay, and what is the shear force along the beam? In other words, what is a shear force? What is a shear force? Like I said, guys, there's no wrong answers. Give me your best.
The force perpendicular to the beam.
The force perpendicular to the beam. Okay. Now, Jimmy, you're half right. Okay, you're half right. You're not completely right, and you're not completely wrong. Fair enough? How's that?
What is the wrong part?
Okay, now look. Okay, let me change colors here. Let me take a blue. Okay. Now, let's say I take part of this beam right here. I take part of the beam right up to here, right? Let's say I take about 2 meters of this beam, okay? So now here I have a reaction of 50 kilonewtons. And here I have a force, a load, I should say, of 10 kilonewtons per meter, right? Now, if I look at that part of the beam, is that beam in equilibrium? If I do sum of f of y, okay, let's take a sign convention going up, positive, okay? Is this beam in equilibrium? Are the sum of the forces in the y direction in equilibrium? Yes or no?
No.
Okay. And why isn't it in equilibrium?
It doesn't cancel out.
In other words, it doesn't add up to zero. Everybody understands what equilibrium means? That when you sum up the force, if it adds up to zero, you're in equilibrium. So now upwards is 50 here, right? Downwards is negative, so minus 10 times 2, right? And that gives me what?
30 kilonewton.
30 kilonewtons. Okay, so if I have a beam here, right, and if it's not moving, and I need 30 kilonewtons to keep this in equilibrium, how is that possible? So that means there's got to be an internal force that has to develop in the beam here of 30 kilonewtons in order to keep this whole thing into equilibrium. And if you look at the shear diagram, that's what that value would be on your shear diagram. So anywhere along the beam, if you want to know what the internal force to keep all the forces in the y direction in equilibrium, the shear diagram gives you all the values that happen along the beam to keep everything in equilibrium. So that's what you're doing with the shear diagram. You're trying to determine what are the internal force that keeps everything in equilibrium. Because once you know that internal force, then you can take that force and see how much resistance does the material have for that force, and then you can actually make sure that the design of your member is sufficient to resist that force, or vice versa. You make sure the member is big enough to be able to resist that force. And then after that, from your analysis, you'll be able to design your beam. Now, so that's for shear. So that means that anywhere along here, wherever I cut this beam, all the values on the shear diagram will tell me what are these internal forces that happen in order for the beam to stay in equilibrium. And when it comes to bending moment, okay, when it comes to bending moment, it's the same thing. In other words, if I look at this section of the beam here, okay, if I look at the section of the beam here, okay, and if I look at this thing is going to want to rotate, oops, sorry. This thing is going to want to rotate around that point, okay? And in order for that rotation to be in equilibrium, I have to have a rotation in the other direction to make it equal to zero, and that's what the moment diagram does. It tells you all the rotations that have to occur into the beam in order for the beam to stay in equilibrium. So what you're actually doing is you're trying to determine all the internal forces that the member has so that it's in equilibrium. And then once you know what those forces are, you can actually take them and design your member with them. And that's what you're doing with analysis. You are trying to determine all the internal forces that a member may be subjected to based on the loads or forces that you're being applying to that member. And that's what structural analysis is all about. And of course, if you have things that are statically determinant, in other words, if you only have 3 unknowns in your structure, you can use simple statics to do your analysis. And when the things are more than 3 unknowns, well, then you have to get into something a little bit more complicated, and that's why we have software, and that's what we're going to learn how to use ADA. So that's the whole purpose of structural analysis, is so that we can find what internal forces our members are going to develop based on the external loads or forces or effects the member is subjected to. And based on that analysis, we'd be able to design the members of our structure. So now, what are the internal forces? Well, you can have a shear force, you can have bending moments, you can have an axial force, okay? So in other words, sometimes you can have, for example, I can have here a rope that's attached to the ceiling, and I hang here a weight. So here I have an axial force, and of course this would be in tension, or vice versa. I can have a floor here, I can have a column, and I can have a load applied on top, and therefore I have a compression force. So these are all internal forces that the member is going to be subjected to. And you can have torsion. Okay, does everybody, have you talked about torsions in physics? Kind of. Well, you know, torsion is when things want to twist. Okay, so that's what torsion is. And of course, okay, so this is the 4 internal loads that develop in, you know, that can develop. They're not all there. Sometimes they can all be there. And sometimes they're, you know, sometimes like some of them, for example, some of them can all be there. And I can show you a very simple example where you would have all forces being present in a beam, okay? Like for example, when you guys were doing your physics, okay, and you had a beam, sorry, and you had a beam here, okay, and you were applying all your loads and everything, okay, and you had this and all that. Well, like if the force is perpendicular to the member here, okay, and the bending moment here and everything, like for example, if I draw a cross section here, and everything happens to coincide with the centroid, which your teacher never even talked about, everything coincides here, therefore you only have shear and bending. But if all of a sudden I have a force here, okay, all of a sudden I have a force here, and this force happens to be at an angle, and it happens to be off center, and therefore this force will also cause axial tension or compression, and will also cause torsion. So whenever the force does not coincide with the centroid of the beam, it will cause torsion. And of course, if the member if the beam is being subjected to a load that's at an angle like this, well, then you're going to have 2 components, and then you can have tension or compression depending on how the thing is being supported, okay? So even in a simple beam, you can have all 4 forces occurring, and of course, you can overcome that by making sure the loads are applied at the centroid. So now, you guys, what are loads, guys? Anybody have any idea what loads are?
Maybe weights that are going to affect the structure.
That's a good definition. Very good definition. Weights. And what do weights do?
I think weights causing some stress on the structure.
Causing some stress on the structure. Jimmy, that is unfortunately wrong. I just want to know what the loads are. I'm not asking you what the loads do to the structure. I'm asking you what the loads are. Like in other words, what are loads?
Is it a type of force?
Yeah, a load could be a force. Very good. And what else can a load be? But Emmanuel, that was you, Emmanuel? Emmanuel, perfect. A load could be a force. In other words, here I have a beam, I represent this as a beam. I have a concentrated load here, and therefore this becomes a force. Perfect, okay? And what else can you put on the beam?
Support.
Well, I mean, like, for example, you guys have heard of, you know, of what's a kilopascal?
A moment.
A kilopascal is a moment? No. A moment, guys, is a force. Guys, so that you know this, a moment is a force times a perpendicular distance. That's a moment, okay? A force times a distance, and therefore the units for moment are a force, kilo newtons, times a distance, and it can be meters, or it can be Newton millimeters, or whatever. So that's a moment. A moment is a force times a perpendicular distance to the force. That's a moment, and therefore the units for moments are kilonewton force times some distance. So now, this here is kilonewtons per meter squared. That's a, that's a kilopascal, or newtons per meter squared. That's a pascal. So what is this? A force divided by?
An area.
Exactly. So in other words, a pressure, okay, a pressure is a force divided by an area, and that gives you a pressure, okay? Now, for example, they say that the floor of the school has to be designed for a load of 2.4 kilopascals, right? So that means that you're going to be putting 2.4 kilonewtons of force on every square meter of that floor area. That's what you're doing, okay? Now, what are the units for stress?
Pascal.
Pardon?
Pascal.
Okay, you can have pascals for stress. Okay, so in other words, stress is a force divided by an area, right? That's a stress. And a pressure is a force divided by an area. What's the difference between a stress and a pressure? If they're the same units, in other words, if stress is pascals and a pressure is pascals, what makes one different from the other? Why aren't they the same? Well, guys, so that you have an idea, like stresses are internal to the member. In other words, it's an internal force divided by the cross-sectional area of your member, where this is an external force divided by the area that's being imposed on the member. And that's the difference. And therefore, when you're doing stresses, you're actually calculating the internal pressures that the member is going to be subjected to, okay? So just that you can have an understanding, like if you ever ask yourself, well, what's in between? So in other words, when I give you a lot of work to do, I'm creating a lot of pressure on you, and what you're feeling inside your body is a lot of stress, basically. That's another way of looking at it, okay? So loads are imposed forces and pressures applied to a structure or system and members, okay? That's what a force is. In other words, the force are all the pressures or all, in other words, you can have kPAs, pounds per square foot. Those are all the pressures that you're going to be imposing on your structure. And, or you can have a concentrated load of 1,000 kips or 1,000 kilonewtons or 1,000 newtons, whatever it is. Those are forces. So those are all the different force or pressures that you're going to be applying externally onto the member, and then of course that's what the loads are. So and if you can also have what we call effects. Okay, now when it comes to forces, there's different types. Okay, and the types that I tend to categorize them in is as follows. And now this is not me, this is also what you would find in the National Building Code. Okay, so you have permanent load. Okay, the permanent load is a load that changes very little once it has been applied. So for example, the permanent load of a structure is considered the dead load of a structure. In other words, whatever is there, the dead load changes very little over the life of the structure, and therefore we call that a permanent load. And then another type of load is what they call variable loads, is a load that frequently changes in magnitude, direction, or location. So this would be your wind load, changes in magnitude, change in direction, change in location. Your snow load can change in magnitude and location. It can be, it can snow more here, more there. And even your variable load that you have, your live load that you have in the house. One day you're sitting in one part of the house, another day you're sitting in another part of the house. So even your live load is considered a variable load. So that's the occupancy load of a room. So the first one is called a permanent load, which is basically your dead load. Then you have your variable loads, which is your live load, your snow load, and your wind load. And the third one is the rare loads that occur infrequently and for a short period of time. So these are your earthquake loads. Now, we're not going to talk about earthquakes in this program. That's beyond the scope of this program, but the rare loads are called earthquake loads. So these are the three types of loads as defined in the National Building Code. Now, when you're actually doing, loads and effects to be considered in the design of a building and its structural members and connections. So these are all the loads and effects that the National Building Code expects you to consider if they're present in your situation of whatever you're designing. And the first one they talk about is, of course, dead load. And that's represented by a capital D, dead load, a permanent load due to the weight of the building components. Okay, so we'll talk about dead loads today. So one of the first loads that's guaranteed to be there is your dead load, because just the weight of the member itself is considered a dead load. And then after that, you have earthquake loads, which, like I said, we're not going to talk about that, but believe it or not, Montreal is in an earthquake zone, and you have to design for earthquake or for wind, whichever is the stronger. And then you have what they call a permanent load due to lateral earth pressure. So when you're doing foundation walls, the earth causes a lateral pressure, and therefore, for foundation walls, you would have to determine what that pressure is and design the wall accordingly. And you also have live loads, okay? A variable load due to the intent, use, and occupancy. We'll talk about that today, the live loads. And permanent effects caused by pre-stressing. So you guys, who hasn't heard what pre-stressed concrete is? Everybody knows, did you talk about pre-stressed concrete somewhere in the past? Okay, so you know what pre-stressing is, and believe it or not, the pre-stressing does have an effect, and you have to compensate for it when you design your member. Then there's what they call the variable load due to snow. We will be doing some snow load calculations in this course, and I'll show you how to do that. That's going to be next week, including ice and associated rain. And then after that, you have effects due to contraction, expansion, deflection caused by temperature changes, shrinkage, moisture changes, creep, and ground settlement, okay? So all of these effects, if they're present when you're designing your structure, you have to take them into consideration. So if you are going to be doing something outside where the temperature is going to be going from -40 to +40 year round, and therefore there's going to be a change in temperature, and these changes of temperature are going to cause additional internal forces on your structure, you have to account for them, okay? And therefore, this is something else you have to take into consideration. And then you have wind, okay? Wind is a variable load due to wind. So these are the loads that you have or effects that you have to consider when you're designing something. And like I said, sometimes only 2 of them are present, so therefore you only have to worry about 2. Some of them, sometimes they can, you know, so therefore these are the ones that you should see if you have to figure out what these values are before you can actually do your analysis, and then of course design your members or your structure. So this is just, like I said, a sum of all the forces and effects that you have to consider for structural members and for a building. Now, dead loads. Let's talk about the very first one, dead loads, okay? The dead load for a structural member consists of, and guys, this is not me that makes this up. This is something that you have to always consider to be able to evaluate when you're calculating the dead loads for a structure, okay? So of course, the very first thing that the dead load is composed of is the weight of the member itself. Does everybody understand what I mean by the weight of the member itself? Everybody clear on this? What I mean by the weight of the member itself? Okay. So for example, you know, like, so you always have to, like, for example, if the member weighs, you have to be able to determine the weight of the member, or you have to, you know, account for it. Now, the second thing that is part of your dead loads is the weight of all materials of construction incorporated in the building to be supported permanently by the member. So if you know that you're going to be attaching other building materials that are going to be supported by that member, that you have to be able to evaluate that, and you have to be able to include that as part of your dead load that the member has to carry. And we'll be doing examples of that today. Now, weight of partitions. Who doesn't know what a partition is?
I don't know.
You don't know what a partition is, okay? In other words, if ever you look at a floor plan, if you look at a floor plan and you have walls that separate rooms in your floor plan, do you understand what I'm saying, Jimmy? These are called partitions. Okay, so if you know that your floor is going to have partitions, you have to include them as part of your dead loads. Okay, so the walls that separate, for example, the walls of your bedroom in your house are the partitions of your house. Except for the exterior wall, I'm talking about all the ones on the inside, okay? So those are partitions. And the weight of permanent equipment. So if you know you're going to have something sitting on your roof or something sitting in a room that's going to be there, like for example, you know, some buildings have, for example, they have generators, they have air conditioning systems, they have furnaces, they have hot water tanks, anything that's sitting on your floor, any of that equipment that the floor is going to have to carry would be considered a dead load. And then this can happen, okay? You can have the vertical load due to earth, plants, or trees. So, you know, some people like to have some nice terraces on top of their buildings, and when they start putting the planter boxes on top on the roof that are going to eventually grow their plants or their trees, well, you're going to have to assess that and consider that to be a dead load to be carried by the roof structure and all the members that are supporting that terrace, okay? So these are the 5 things you always have to keep in mind, okay? Like I said, sometimes this might not be there, that might not be there, that might not be there. This is guaranteed to be there. Sometimes it, you know, so you have to assess this and be able to estimate what the dead load that the member will be subjected to. Any questions so far? Okay. Now, live load due to occupancy. Now, guys, this here, okay, is not very difficult because if you go to the National Building Code, the National Building Code has a table that gives you the minimum live load that you have to subject your structure to, depending on how it's going to be used. Now, I don't know. Okay, so the National Building Code of Canada requires that the live load shall not be less than the values listed in table 4153. Okay, and of course, this I don't know if this is clear to everybody. I should have maybe. Okay, is this clear to everybody, or is it hard to read? Now you see what the National Building Code does, okay? And I'll go through this, okay? So for example, assembly areas. In other words, where people are most likely to gather and, in groups and, stand around, okay? So for example, in arenas, auditorium, churches, dance floors, dining areas, foyers, grandstands, gymnasiums, museums, promenades, rinks and all that. Well, they want you to use a minimum live load of 4.8, and here's the units, kPa, okay? So this is, if ever I'm designing a restaurant and I want to know what kind of a live load do I put to design the floor of a restaurant, well, a restaurant is a dining area, and therefore I would apply 4.8 kPa as one of my design requirements. Now, and like I said, guys, this is, see the word here, minimum? It's not a maximum, it's a minimum. Now, if you decide to use these minimums and something still goes wrong in the future because it happened to go over that minimum, believe it or not, you're still responsible. Because with the way that they define this is that it was up to you to judge whether that minimum required by the code was sufficient in your particular case. And if you thought that you needed to have a little bit more, you should have put more. Okay, so keep this in mind. These are not maximum values, these are minimum values. Believe it or not, all of the school was designed for 2.4 kPa. In my days, this was 100 pounds per square foot. This was 50 pounds per square foot because we used to work in Imperial, okay? I don't know if you guys are familiar with the Imperial units and so on. Now here is portions of the assembly area with fixed seats. So if you know you're gonna have fixed seats in an arena, you can go from 4.9 down to 2.9 if you want, or you can leave it at 4.8, okay? And lobby corridors, okay? So what this means is that at Dawson College, for example, okay, here's the building, okay, at Dawson College. Here's a classroom, here's a classroom, here's a classroom, here's a corridor, okay, and here's the other corridor, and here's the other classroom. So at Dawson College, what's going to happen is that when the guy's designing that floor, here in the classroom, he's going to be putting 2.4 kPa as the live load in the classroom. But when it comes to the corridors, he should be putting 4.8 kPa, because what happens when everybody walks out of the classroom? Well, are there going to be more people in the corridor than there are in the classrooms? The answer is yes. And that's why the National Building Code requires in corridors, you go back up to 100 pounds per square foot so that you can account for the fact there's going to be more people gathering in that little area of the building. And therefore, the floor would be designed for 2.4 kPa in the classrooms and then 4.8 in the corridors. And some people tend to, forget that. And that's the way you're really supposed to be designing your floor. So if all of a sudden if there's a member supporting the floor here, it's going to have a higher load than the member supporting the floor here. So that's what they want you to do. Clear. Okay, now attics. Does everybody know what an attic is? Or who doesn't know what an attic is? Guys, don't feel shy. Now's the time to ask, understand? So if you, like, an attic is a roof space between your ceiling and if you have a slope roof, you understand? Like this, well, the space up here is considered an attic, okay? And of course, this is, if you have stairs leading up to it, here's one thing and so on. Now, exterior balconies, they want you to design them for 100 pounds per square foot, okay? Corridors, 100 pounds per square foot, and so on. If you get into mechanical rooms, they want you to design it for 75 pounds per square foot. I used to know all these like from my, now I have to get to learn in kPa. Exits, 100 pounds per square foot, you understand? 150 pounds per square foot, 6 kPa for footbridges. Okay, garages, 4.8 kPa, garages, okay? But now what I find interesting, okay, if you have for vehicles not exceeding 4,000 kilograms. So all the internal garages that you see in buildings, and even the ones that, like when you go inside an indoor parking structure, okay, believe it or not, that floor area where your cars are actually driving on and they're actually parking on are only designed for 50 pounds per square foot. Okay, and that's if the vehicle does not exceed 4,000 kilograms, which is fairly heavy because a car usually weighs about 1,500 kilograms, not more than that, okay? And so on. And of course, here, I mean, if you know that you're gonna have some heavy trucks, okay, if you're gonna have some heavy trucks going into that area, then you have to go all the way up to 12 kPa, which is about 250 pounds per square foot. So now, if you have kitchens other than residential, 4.8. So this is where you have to look at all the rooms that are going to be used in your building. So the architect would say, well, here, this one's going to be a commercial kitchen. This is going to be a dining area. This is going to be this. So you would have to come here, come to the table. So well, this area has to be designed for a minimum of so much. That area has to be designed a little so much. And this is where you get all your occupancy loads that you're going to be using to do your analysis so that you can design the floor accordingly, okay? Look at libraries with stacks, 7.2. So if you're designing a school and you know that a library is going to be part of that building, that area has to be designed for 7.2 kPa if it has stacks. Now, the areas where the architect decides to make only a reading area, well, then you can go from 7.2, you can go down to 2.9 if you want to, or you can design the whole thing for 7.2. It's up to you. Operating rooms. Now, billiard rooms, bowling alleys, and pool areas, 75 pounds per square foot. And this is one that you guys should get to know because when you're designing the live load for a house, for residential areas, okay, a house is considered a residential area, whether it's a bedroom and whatever, even for stairs, everything in a house is designed for 1.4 kPa. So in other words, this is 40 pounds per square foot. And that's the live load that you will be using to design, whether it's your floor, whether it's your stairs, whether it's the corridors, they all get designed for 40 pounds per square foot. And that would be the live load that you would be applying, okay? Now, here's something interesting that I want to highlight here, roofs, okay? Here they say your roof should be designed for 1 kPa, but that's minimum. So for example, we know that here in Quebec, it snows and therefore we have to calculate the snow load, and we'll do that next week. And if the snow load happens to be more than 1 kPa, then we have to design for the higher of the two. And all of a sudden, if I design something that has less than 1 kPa, I have to at least apply always a minimum of 1 kPa to the design of a roof, okay? I can't go less. Why do you think they specify a minimum? Like for example, in the summertime, when there's no snow, why do you think they want to have at least 1 kPa minimum for the roof design?
For the rain?
Oh, there's also a rain load. So the National Building Code requires you to determine whether the snow load or the rain load is going to be the higher, okay? But I'll give you an example. Let's say, I'll give you an example. And this is going to be easy, but I'm glad you brought up the rain. So that's a good idea, but not necessarily the case. Let me give you something very simple, okay? Let me clear the drawing. Okay, now, here, like, you'll see this next week, okay? Here's a roof like this, okay? Okay, this is a roof. And the angle here is 75 degrees, okay? And if you're gonna do your snow load calculations for this angle, the snow load ends up being 0, okay? So if there's gonna be no, and then of course, you know that the rain's never gonna be accumulating on this. So if you know that the rain load is 0 and the snow load is 0, why do you have to still design it for 20 pounds or for 1 kPa?
To resist the wind load, maybe?
The wind load? The wind load is going to be in this direction, okay? It won't even be vertical. And that means that, okay, so do people go up and maintain the roof sometimes? So for workers to be able to, be able to get up there and make sure that they have something that's relatively strong enough to support them, that's why we design for at least 20 pounds per square foot, okay? So that's the minimum load that any structure should be designed for. And Jimmy, I'm glad you brought up the wind. If you do a wind load calculation here, and if it's even more than 20, albeit, but if it happens to be less than 20, and most likely it'll be less than 20, you always have to design for a minimum of 1 kPa, okay? So that's something I want you guys to keep in mind. And of course, warehouses and so on. So this is, like I said, guys, I don't memorize this table. Whenever I'm designing something, I take out the National Building Code. Even though I know them by heart, most of them, I still go back and make sure I'm using the right value. And again, if I see that a situation is very particular and all of a sudden that this minimum required by the National Building Code, I think that is not sufficient, there's nothing that can stop me from increasing to make it even higher. Okay, so I'm allowed to double these loads if I want to feel more comfortable that that's what it should be. Okay, and when I do that, the only person that pays for that decision is my client that's going to pay for a better structure. That's all it means. Okay. So, any questions on these two tables? Okay, so like I said, straightforward. You simply, get yourself, like you're gonna have a copy of this one. I'm gonna be sending it to you, but this is basically where you come and get the information and you use this information to do your analysis. Now, the calculation for the specified dead load is the best estimate of the actual loads a structure is expected to carry. Remember, I want to stress this word here. Best estimate, guys. When you're calculating, when you're trying to estimate dead loads, you'll never get an exact value, okay? In other words, I can estimate dead loads, you can estimate dead loads, okay? And if we happen to get the same number, it's a coincidence, but it's always what they call the best estimate of what I can think that the dead load should actually be. Okay, so keep that in mind. You're just making an estimate and trying to make it as accurately as possible. Okay, there's no exact value for dead loads. If somebody says, "Oh," and I don't want to get into it, but like for example, when I'm doing a concrete structure, okay, I take the unit weight of concrete to be 23.6 kilonewtons per meter cubed. But when they're actually going to batch the concrete, it can be 23.5, it can be 24, it can vary. So even at that, even though I've estimated concrete to be 23.6, there's no guarantee that that's going to be the actual unit weight when they actually deliver it, you see? So that's what they mean by it's the best estimate that you can make of your dead loads. So now here, I'm going to give you an example, and if you guys want to copy this down, you're more than welcome to do it. I mean, I'm going to be sending you the file, so it's up to you. So basically, when you're trying to calculate the dead load, okay, when you're trying to calculate the dead load, so for example, here, I'm going to give you an idea of what's happening, okay? I have a building, okay? This is the building, okay? And right now, I don't know, I'm just, okay? And right across here, okay, I have these members that are running across like this. And this is what they call an open web steel joist. Okay, so in other words, this is an open web steel joist here. And these members are very, very, used very, very currently in steel structures to carry, either a roof load or a floor or whatever. So that's what these are. And then, of course, this is what the architect decides to put on top of the roof. You can put insulation, you can put a membrane, you can put whatever he needs to put on. And what you're gonna, you as a designer will have to calculate what the load that this member is going to be carrying, so that eventually you can actually design the open web steel joist to be able to support that load. So when I'm talking about roof assembly, okay, that means that the architect had decided to put a 5-ply asphalt and gravel roof Does everybody, I think, do you talk about roofs in construction 1 or construction 2? Kind of. Do you understand what I mean by a gravel and asphalt roof? Has anybody ever gone up on a roof? A flat roof? Okay, so next time what I should do is, had I known, I would have gotten a couple of pictures from the internet. Basically, most flat roofs have a ballast, which is like a gravel, okay? And then underneath that gravel, they have a membrane, and that membrane could be made up of an asphalt built up, and they put a sheet of tar paper. They didn't talk about built up roofs in construction 1 or construction 2? Emmanuel, if you're trying to talk to me, you'd have to take your speaker off. No? Okay, so guys, anyways, look, I apologize. I thought they talk about roofs and construction 1 and construction 2. That's why I didn't want to bore you guys by repeating it here. But basically, I mean, we can do this at the end of the day. If we have time, we can go to the internet and look at examples of built-up roofs. But basically here, what happens is that the architect would tell me, well, this is what I'm planning to do. I'm planning to put a 5-pile asphalt and shingle roofing. I want to put 300 millimeters of rigid insulation. Then I have a steel deck that's going to be running this way across the joist. These are open web steel joists I was telling you about, okay? And then after that, the architect wants to close the ceiling with a gypsum board, okay? With a gypsum board that's going to be attached to the open web steel joist. So you want to be able to calculate what's the dead load that this joist is carrying, okay? And now you ask yourself, well, where do I start, okay? Well, what you have in a lot of books, okay? and even if you go on the internet and you type in, you know, dead load of materials, you might even find more examples. I took this one here straight. I took this one straight from the my steel handbook, okay? And this is what you find in a lot of handbooks. What they do here is they give you, for example, values of what design dead loads of materials. So for example, steel decks. You guys might not know what a steel deck is, but a steel deck is a corrugated sheet metal that they put on top of joists. And I should have maybe got a picture of that also. And concrete, I don't even use this myself. I'll show you a fast way of calculating that. The joist, plywood, if the plywood is 11 millimeters thick, you should assume that it weighs at least 0.06 kPa and so on. Chipboard, which is an OSB board, which is a little bit heavier than plywood. This is for bricks and so on. Oops, gypsum board. Okay, gypsum board. And here's floor finishes. So for example, if you have a hardwood floor, this is per millimeter and so on. So here, this is a good table that you can start getting values of how to calculate the dead load of the materials that the member is carrying. So like in our case, we have the very first one, we had like a 5-ply asphalt and gravel. We had 5-ply. Now here they give you one for 4-ply, 3-ply, 4-ply. So you know that if you want, you can take this information here. In other words, this is 3-ply with gravel. This is 4-ply with gravel, okay? And if you look here, this is a 3-ply with no gravel and a 4-ply with no gravel. So if you see here that each ply of asphalt that you put down increases it by 0.05 kPa. So if I know that a 4-ply is 0.32, and I want to estimate what a 5-ply might weigh, well, I would just simply add 0.5 to it for the 5th ply, because the gravel weighs the same, and therefore a 5-ply would weigh 0.37 kPa. So that's where I would get the information to estimate the dead load of that roofing, okay? So clear drawing. Okay, so here, when it comes to the 5-ply asphalt and gravel, like I said, from the table, I was able to guesstimate or estimate that that's going to weigh 0.37. Then after that, 300 millimeters of urethane insulation. Okay, so here I go back to the table and I look for insulation. Now, I have rigid insulation here. Now, keep in mind that this table has constraints. In other words, this is per 100 millimeters here. Okay, so therefore, if I know that this is only for 100 millimeters, and I have some rigid insulation here, which is 0.3, so 0.3 kPa per 100 millimeters, and then I multiply this by 300 millimeters because that's what I actually have. Well, I know that I'm going to end up with 0.09 kPa. So that's how I estimate the. I keep doing that. So that's how. So for the rigid insulation, I go to the table and I find that for 100 millimeters, it weighs 3 kPa, and of course for 300, it would weigh 900. Then after that, I have the steel deck. So the steel deck is 38 millimeters thick and 38 millimeters deep, and therefore, if I see if I can find a value here in the table. So I look at steel deck here, okay, and they're suggesting that up to 1.91, that I can use 0.10 kPa. So therefore, I'll use 0.01 kPa, okay? Now, the other thing, gypsum board, in other words, there's a sheet of gypsum board. So therefore, if I go back to the table here, I look at for gypsum board, and I think there's a couple of places where they have gypsum board. Like for example here, gypsum wall board per 10 millimeters. They suggest that you use 0.08 kPa for 10 millimeters. I think there's somewhere else where they show gypsum board. They're showing at least 2 places in this. Yeah, here, gypsum board, 10 millimeters, 0.08 kPa. So I'm going to do the same thing. This is for 10 kPa, for 10 millimeters, and then for 12 millimeters, I increase it to about 10. Now, the open web steel joist, at this point here, I haven't designed it, so I'm going to have to assume something. So I'm going to assume that it weighs 0.1 kPa. And that's, I'm going to check that afterwards, but I always have to include the weight of the member itself. And then after that, I have the 15.5 millimeters of gypsum board. So I do the same thing as I did before here. I take 0.8 per 10 millimeters, multiplied by 15.5, end up with 0.3. Now, there's one last thing here that you guys don't see, the architect won't show because it's not part of his design, okay, is what else do you think that this joist would be supporting permanently during the life of the structure? Does anybody have a guess? What other things do you think this member should be carrying or will be supporting when the building is going to be constructed?
The chimney, maybe?
The chimney?
Yeah.
No. There's no chimney in this building, so I'm not worried about that.
No?
Snow is not a dead load. Snow is a variable load, and we'll talk about that next week. We're just talking about dead loads. In other words, materials that are going to be permanently attached to my member, and therefore I'm trying to estimate what the dead load is. Oh, and in a way, guys, how do you say dead load in French? Does anybody have an idea how to say dead load in French? Nobody has an idea how to say, if you're talking to somebody in French, you want to talk about dead loads, what would you say? First of all, how do you say loads in French? Does anybody know how to say loads in French?
Poids.
Sorry?
Le poids.
Poids is more like weight. Oh, guys, don't like. I'm gonna do this because in Quebec, you know, there's a good chance you'll be talking to somebody in French, and therefore you might as well use the right terminology. In French, a load is called une charge. Okay. Now, a dead load in French is not une charge morte. That's just a translation from English. In French, when we talk about dead loads, they call it une charge permanente. So whenever you hear the word charge permanente, that's dead load, and it's like permanent loads. And I like that term better in French than in English. And therefore, in French, dead loads are called les charges permanentes, and that's how you say dead load, okay? Now, so what other dead load would this member here be carrying? Are you guys at home right now?
Yeah.
If you look up, what's attached to the ceiling?
The light.
Okay, so you think there are going to be lights in this building?
Well, yeah,
So
most likely.
how are they going to be supported?
The ceiling.
Pardon?
Uh,
They're going to have to be attached to this somehow, right?
yeah.
Do you think there's going to be a sprinkler system in this building? Okay, so
Yes.
how is that sprinkler system going to be supported in the air? It has to be supported by this member, okay? Do you think there's going to be some ductwork or some ventilation that's going to go through the ceiling, okay? So all of this mechanical, electrical equipment that you don't see here right now, okay? You can't wait until it actually gets designed. What you normally do is you make an allowance for it so that you compensate that in the eventuality that there's going to be pipes, there's going to be wires, there's going to be light fixtures, there's going to be this, there's going to be that. You've already accounted for it in your dead load, and therefore you know that your member is going to be able to safely carry that additional weight. So here, if you look here, what they suggest here, okay, is, for example, if you look here, I'm going to show you here on this table here, okay, on ceilings, okay, allowance for ducts, wiring, and pipes, okay, they suggest that you allow for 0.25 kPa. Now, sometimes this could be reasonable. In other words, this is like 5 pounds per square foot, which is a reasonable, you know, guesstimate, okay? This is about 5 PSF. And if you don't think that this is going to be enough because there's going to be heavier pipes or bigger equipment and all that, you can always increase that. And if you think that there's going to be very little mechanical, electrical in your ceiling, you can even reduce it. So here, this is an average condition. Remember that this is just a guesstimate, okay? And you should always make some kind of allowance because you know eventually there is going to be at least, you know, at least your water pipe or at least your wiring and your light fixtures. So here, what they're suggesting as a minimum to add 25, you know, 0.25 kPa to allow for the eventual ducts, pipes, and wiring. So I you know, like, I think that this is reasonable for a standard building, but then again, it's up to you to judge whether this is enough or if you think that there should be more. If there's nothing to stop you from using 0.5 kPa. There's nothing to stop you from using 1 kPa. It's up to you. You have to judge, but this is a good starting point, okay? So that's the last thing that that member is going to be carrying. So therefore, Now, what you basically do is once you've, written, like what I like to do, guys, when I'm doing this thing is that I like to look at, I try to be systematic. I can either start from the top and work my way down, okay, and list all the materials that I'm going to be trying to find the loads for, like I did here, or start at the bottom and work my way up, and try to be somewhat organized when you're doing this so that you don't skip anything. And then go find these values here, even like the table like I have here. And if I can't find it in the table, I'll go on the internet. And if I can't find it on the internet, I'll find a way to estimate it. And then you simply add them all up. And this ends up being 1.14 kPa. Now, you can use this value here. You can round it up to 1.2. You understand? Like, in other words, if you want, you can say use 1.2 kPa. Don't round down. If you're going to round your loads, always round up, not down. Okay. And that would be like a good estimate of the dead load. That this is about 20. I think this is about 22 to 23 pounds per square foot, which is a reasonable dead load for an industrial building. Does anybody have any questions?
Yeah, do we always calculate per square foot?
I do, Emmanuel, because I love, like, to me, I have no sensitivity of what a kPa is. You understand? Do you?
Not really.
And so, like, but I do have a sensitivity when I say 22 pounds per square foot. Do you follow? That's so therefore what I do is I tend to convert this into pounds per square foot, so I have an idea if I'm in the right ballpark. Now, if you want to know how to convert this pounds per square foot, it's very simple. Okay, 1 pound per square foot. If you guys want to write this down, the conversion factor, you can just convert it. Okay, is equal to 47.88. Now this is in pascals. Okay, so don't forget that this here is 1,140 pascals. So if anybody's got a calculator, if I take 1,140 divided by 47.88, yeah, this is about 23.8 pounds per square foot. Okay, so that's the conversion factor from pascals to PSF. And that, when I said it was about 22 to 23 PSF, I was in the ballpark. If I want to know exactly, I would do this quick conversion on my calculator. So that's how you convert. Guys, to give you an appreciation, you guys, you heard of a Newton? So does anybody have any idea what kind of a force a Newton is? Well, a Newton is approximately, you guys go to McDonald's, do they still sell the quarter pounders at McDonald's? Huh? So a Newton is approximately a quarter pounder from McDonald's. So when they say that the load is 10,000 Newtons, just think of 10,000 hamburgers being stacked up. That's the force that's caused by. So a Newton is about the quarter pounder of McDonald's. Okay, and that's how I get a sensitivity of, like, for example, the column is carrying 2,500 kilonewtons, so that means it's carrying 2,500,000 hamburgers, and that gives me an idea. Yeah, that's a reasonable load. Understand? So that's how I tend to. Okay, so that's the like I said, that would be the dead load that the member has to carry, and then of course in this course we're going to take this and be able to convert it and do the analysis if we need to do the analysis with it. Now, here's another example, I believe. Okay, so in this case here, I gave an example of a simple residential floor. Okay, now in this floor here, okay. I don't know if you guys can see this, but in this floor here, I have an oak floor, 20 millimeter oak floor. Okay, I have a plywood subfloor. I have the joists themselves, and then I have a gypsum board that's sitting or supported on the ceiling of this floor. So in other words, this would be somewhere in a bedroom. Then they have the floor joist supporting the floor of the bedroom. I have a subfloor that's 19 millimeters thick, which is a little bit thick, but it's okay. And I have a gypsum board in my basement that covers everything and gives me a nice finish in the basement. So if I want to be able to calculate the dead load that one of these joists is carrying, or the joists that are carrying, I do the same thing. I simply, I go back to the slide here, okay? So I look at floor finishes. Here I have vinyl floor, okay? Now hardwood floor per 10 millimeters. In other words, oak is a hardwood, and this is per 10 millimeters here. If it was carpeting, I would use this value here, okay? Carpeting, they're suggesting you put 2 pounds per square foot or 1.1 kPa. So they're saying that when you're doing a hardwood floor, they suggest that you use 0.08 kilopascals, but this is per 10 millimeters, okay? So if I look at the 0.08 kilopascals per 10 millimeters, that gives me 0.16 kPa. So that would be just the weight or the dead load caused by the floor here, the oak floor. In other words, now for the plywood itself, well, I would go back, see if there's a value in the table. So, oh, here I have one. So here I don't even have to interpolate or anything. They're suggesting that for a 19 millimeter plywood. Now, what happens if I would have a 16 millimeter plywood? Well, I would interpolate between these two values. You understand? In other words, if 19 is equal to 0.11 kPa, 16 is equal to X, and therefore I would cross multiply and get an approximation of what the 16 would weigh, okay? As a matter of fact, if I do this the other way, if I do 19 is equal to this divided by 11, I should I should end up getting 0.8. So for 19, they suggest that I use 0.11 kPa for the weight of the plywood. So here I get the value straight from the plywood. Then the wood joist. So this is 38 by 235. Now, you guys might not realize this, but when you're talking about wood joists, okay, first of all, does anybody know what a wood joist is? Have you guys talked about joists in construction 1 and construction 2? Have you? Okay, so tell me what a joist is.
It's a plank of wood.
It's a support for the ceiling.
It's a piece of lumber, right? And these lumbers get fabricated in a certain size. And of course, right now in North America, they're still being fabricated in the imperial size, okay? So a 38 by 235 would be 2 inches by 10 inches. Okay, so this is the nominal size. And then in the metric size, you would call this a 38 here, millimeters by 235. So that's what that is, okay? And of course, that's the cross-sectional area of the lumber. And this is how they're being spaced. That means that the distance between here and here, this is 400, 400, and all along the floor, at every 400 millimeters, at every 16 inches, one of these members would be placed to support the floor. Okay, so now you want to know what's the self weight of these members. Well, if I go back to this table here, because this is the way the member itself, you'd have to go back to this table here. And the reason why I like this table, they do give you an idea of what the joist weighs. So if I go down here's wood joists spaced at 400. This is for 184, 235, and 286. So therefore, this is what I have. And they're suggesting that the self-weight of the joist, you should assume 0.12 kPa. And that's where we get the value for the wood joist. So that's where I get that straight in the value. And then of course the gypsum board, we saw this before, so I just go back here, look for the value of the gypsum board. And of course I have somewhere I can find it in the ceiling gypsum board. Per 10 millimeters of gypsum board, that should weigh 0.08 kPa. So I can go back, and therefore for this would be 1. Now here in a residential house, you know that you're not going to have a sprinkler system. You know you're not going to have ducts. You know you might have a little light fixture somewhere. Okay, and if there are partitions on the floor, you have to make an allowance for the partitions. Okay, so here I've allowed the minimum, the allowance that's required by the National Building Code. So if I don't know where the partitions are going to be going on the floor, and they're only going to be built after the tenant walks in because it's an office building, the National Building Code requires me to make an allowance of 1 kPa for the future partitions, which is substantial, but it doesn't hurt to put more than less. Okay, so this is something that you don't see here, but you have to remember that eventually partitions will be built on this floor, and therefore we have to make an allowance for it. And when it comes to office buildings, the minimum load that you have to put for partitions, if they're not there, that the architect had already laid them out, is 1 kPa. So this is, and that's where you get this from. And of course, once I add that up, so this whole thing would come out to 1.49. And to me, that would be totally ridiculous. I would use 1.5 kPa dead load for my floor. So that's about 30 pounds per square foot, which is a reasonable load for an office building that's going to be made out of a wood structure. Does anybody have any questions? How are we doing time-wise, guys? 11:24. Okay. And guys, that's it. Okay, so guys, like I'll repeat this again. Like I said, the assignment, I've already scheduled the assignment to be delivered to you guys by 11:45 today. Okay. You should be using a lab period to work on the assignment. Okay. And I give you instructions on how I want you to submit the assignment. In other words, when you submit the assignment, guys, and I'm going to expect this from you guys, I say it on the assignment, but I'm going to expect you guys to, you understand? You're going to convert into a PDF. I want you to put your family name. I don't care if you don't put your first name, and then you put, ASSGN1, and that's all I care. And of course, if it's a PDF, this will end up being a PDF. So this is how I want you to name the file, because this way, when I store these files in my folder, I'll have them all in the alphabetical order that I have them on my my student list, and it's much easier for me to enter the marks that way. So I would greatly appreciate if you just put your family name, your surname, or your given name. I'm sorry, your given name here. I don't care, but I want to see your family name. Then of course, assignment number 1, and then I'd like it if you can send it to me as a PDF. And as I said, there is no right or wrong for the assignments. I just check to see that you've done them, or you had attempted to do them, and I will give you, as long as I see that I believe that you tried doing the assignment, and if you've done it completely, and even if it's not correct, you will get full marks for it. And I don't know if you guys took the time to read the course outline, but the assignments are going to be worth 5 marks. And at the same time, the assignments are going to be added towards your final grade. So, I'm sorry. And the assignments are definitely going to be helping you to prepare for the exam. So, and you will be getting a typical question like this on the exam. That's going to be one question, and then you're going to get like, and I'll let you know how many questions there are. So this would be one typical question that you're going to be getting on the very first test. So you might as well start, getting familiar on how to solve this problem. And clear all drawings. And that's it, I think, for today. Yeah, so let me just stop the recording so that we can minimize, stop sharing. Okay, let me